so so yesterday we saw a little bit, we talked about jets, the somehow first jet definition of Sterman Weinberg. And so what I want to show you here are, for instance, event displays of jets now. So the one that you see on the left is really a very, very old event display. And this was in fact used as a first really direct evidence for the existence of gluons, because when you have a plus minus collision, you produce QQ bar here, and when you have a gluon, this gluon can give rise to this third hard jet. And this is what you see here somehow, these three, you can see clearly here, here, and here the presence of this kind of three jets. What I'm showing on the left is instead now a dijet event and really high PT, high invariant mass dijet event measured very recently in CMS. So jets are still used today really a lot. Today we use different jet definitions, and I will tell you a little bit more tomorrow about this. But really they are very instrumental for QCD, so they have been used to test QCD in different aspects. And even today they are very useful also as a probe for new physics and for also QCD measurements. Now, one of the reasons that makes these jets useful is the fact that you can calculate them. And as I told you, this fact that you can calculate them is related to this property of infrared safety. Yesterday, I did not write down a definition of what is something that is really infrared safe, so let me write it today. So you take an observable, let me call it O, that depends on your momenta, K1, your final state momenta, K2, and then it depends on two, let me call it Ki, Kj, Kn, okay. So this should go to the same observable, K1, K2, Ki plus Kj, Kn. Whenever Ki and Kj become collinear, or one of the two becomes very soft. So in the limit in which the two emissions are exactly collinear to each other, your observable should not be able to distinguish whether this collinear splitting occurred or not. So should be insensitive to collinear or soft splittings. Now, as an example, you could, of observables that we can discuss whether they are safe or not, you could take an event and then look at the energy, for instance, the energy of the hardest particle in the event, the hardest. Now, is this infrared and collinear safe? Well, it's infrared safe in the sense if you have a soft emission, the hardest particle will remain the same. But obviously, if this hardest particle will undergo a collinear splitting, where it splits the energy into, say, equal components, somebody else could become the hardest particle. So this is an example of something that is not collinear safe. Also, if you talk about, for instance, multiplicities, when you really measure how many particles you have, obviously these are not infrared safe quantities. While things that are infrared safe have to do with measuring, say, energy or momentum flow in a given region of phase space. So for instance, a cone or a rapidity and azimuthal angle region. These are sort of all infrared safe. Now, in terms of jets, I told you Sterman Weinberg jets are infrared safe. And what happened in the past is that many jet definitions were used that were originally not really infrared safe, and then people understood that they cannot really use them to do calculations. And these, in fact, were dropped. Were used a lot at the Tevatron, but now not anymore at the LHC. Now, other observables besides jets that somehow, if you want, characterize the final state, are also very crucial, very important in QCD, are so-called event-shaped observables. So here you don't really build the jets, but you try to sort of project out the kinematics that you have in an event into a single number, and the value of this number should tell you whether your event is more sort of pencil-like or more free-jet-like and so on. So one of the really most known is maybe the thruster, which is written down here. So what you do here is you take an event, you project all the momenta You find a direction where the projection of momenta is maximized, and the thrust value is the projection of that. So here, for instance, in this event that you see here, this one, you will see that all radiation is aligned along this axis here. So when you project along this and then normalize, you will get a value that is very close to 1. But an event like the one on the left here, this one, will give a thrust value that is far away from 1. So somehow the value of these event shapes tell you something about the radiation that occurred in the event. And there are many variations of this. Now they are listed here. Many of them are also used really quite a lot. For instance, now a lot of discussions have to do with energy-energy correlations. This is also, people are interested in this type of observables also beyond QCD. But as you see also in this, on the right column, you see that not all of these observables were really infrared safe, you see. So not infrared safe means that you cannot compute them, or maybe they break at higher orders. Maybe you can compute the first correction, but then they break, the calculation breaks down at higher orders. Now, what does it mean if you try to compute something that is not infrared safe? So technically what happens is that if you do a calculation, you see that you have to put a cutoff, otherwise you don't get a finite result. It might be that numerically this is not very important, you can still maybe implement it in Monte Carlo, but then per se the calculation is not really meaningful. Experimentally, what does this mean that you measure something that is not infrared safe? It means that your measurement will depend on the resolution of your experiment. For instance, the thresholds that you have in seeing, for instance, very soft radiation. Okay. Now, yeah, just to close a bit this topic, just would like to show you how these observables have been used. For instance, this is the thrust that I mentioned. And you see that close to 1, the distribution here, the data increases a lot, because close to 1 is the region where you're dominated by soft collinear emissions that in QCD are enhanced. So the cross-section rises there. But what is interesting, you see that you can compute this now in perturbation theory. And you can, for instance, compute it in a theory where the gluon is a vector, or in a theory where the gluon is a scalar. And then data really could establish that the gluon is in fact a vector particle, as we know today. And here it's another example of another of these variables. And again, you can try to see whether QCD is in fact a non-abelian theory that we talked about, or is related to somehow a copy of QAD and abelian theory. And again, you can do calculations and you see that data really nicely tells you. Similarly, you can use these things, this is now shown here, to fit, for instance, the color factors, the Casimirs of CACF. You see that you can fit, and these fits are really compatible with QCD as we have it today. So this concept of infrared safety at the end is really very important, because this means that you can compute things more and more precisely the more orders you compute. And when you have a theory prediction, you can compare it with data, and then you can extract information. So, yeah. So this is somehow closes a bit this chapter that I talked about in infrared.
Giulia, there is a question.
Yeah, good, because I'm wrapping up this, yeah.
Please.
Yeah, just a question about the table and infrared safety. There were some values in QCD calculation, which were order alpha to some power resummed and other non-resummed. What is their main difference?
Okay, so what does this really mean? So this, okay, I have to say this is not a very new table, but what this means, it tells you at what order this observer has been calculated in QCD. So you see this has been, for instance, calculated at order, say this one, at order alpha s squared. This is what we call next to leading order, alpha s squared, so two loop correction. In this case, you see there is resummed, means that, so as I told you, here in this region, this is the thrust. Here, if you do a fixed order calculation, you will get a log alpha s log squared of 1 minus t. So a fixed order perturbative calculation really here is divergent. So diverges somehow more. When you resum the calculation, you get a finite so-called Sudakov peak. So this becomes an exponent of e to the minus these logs. And okay, here data are not very precise, so you don't see. But if you would have more data in this region, you would see that then data here go down again. So the physical spectrum here goes to 0. And so this is some of these result calculations here. So some of these observables are more simple from a so when you result calculations, often these calculations were done by hand, and those that are simpler could be resulted. Those that are more complicated, we don't have a result calculation. Now, these are computed to even higher orders. But the point is that the point I wanted to make here is that if you have something like this, you cannot really do a higher order calculation. You can compute the leading order, but then that's it, because your result is divergent. In some cases, also, the divergence appears at higher order. So it might be that the divergence appears only at 2 loops, and then you can still go maybe next to the leading order calculation. But obviously, what you want is something that is finite to all orders. And this is also in terms of jets, this was really a big discussion, because at the Tevatron, they used for a long time, maybe I will mention this a bit tomorrow, they use this kind of algorithm called the midpoint cone algorithm, and these were not infrared safe. To higher order, so one could do maybe next to the linear order calculation, but then the next order was really not well defined. Did this answer the question? I hope so. Are there other questions? Maybe there's one more. Yes. Okay. Okay, so this closes a bit what I wanted to say about the infrared behavior. So we saw there are these soft collinear divergences, they arise, but if you're sufficiently inclusive, they cancel out. In this cancellation, the leftover can be these large logs that you get, and in that case, you have to do some calculations. But yeah. Now I want to move to different topic, which has to do now to covering what happens when you have initial state. Now, so far we always talked about the plus and minus and radiation from the final state. But of course now we have the LHCs, the main collider, so we really care about radiation from, we have protons that collide, and the protons of course contain quarks. And so we want to see what happens once you include this in your picture. So schematically, one could think about this in this form. Let me draw here this. So you could think that you have this is my incoming one proton. From this, I pick one quark. Then I have another one, I pick another. So these are my protons, P1 and P2. And here then I pick some patterns, and this produces then, for instance, could be associated Higgs, Dirichlet event, something like that. So the picture that one could write, what is called the so-called Parton model. So the formula in the Parton model is very simple. It says, well, the cross-section for this, sigma, is equal to an integral in dx1, dx2, f p1 of x1, f maybe I do put some indices ij of x2. Then I have a Platonic cross-section. I explain exactly what I mean by this, what is the notation. So x1 and x2 are the energy momentum fractions carried by the partons that enter the scattering. S is the center of mass energy of the collider, so 8 TeV, 13 TeV, and so on for the LHC. And the Platonic center of mass energy, so the effective one that enters the hard scattering is this S hat, which is x1, x2 times S. Now, this formula essentially means that, well, somehow it has a bit of probabilistic interpretation. You pick up a parton with a given probability f x1 or f x2 with a given momentum fraction, and then you integrate over all possible values of x, because of course you cannot determine the energy of it. the incoming particle that enters. So these objects here, these ones, and these ones are what we call parton distribution functions, or PDFs, typically PDFs. So these are really non-perturbative objects. We cannot compute them in perturbation theory, and they are extracted from data. And I will explain a little bit how they can be extracted from data. But they are non-perturbative. While this is somehow our hard scattering cross-section. So this is the Platonic cross-section. This is the Platonic cross-section. And this somehow here, for this part of your calculation, you can use perturbative QCD. As we did for the final state, only you have now incoming and outgoing particles, but you really use your Feynman rules. And so this is the part that you compute in perturbation theory. Now, I said that these Fs are non-perturbative objects. We cannot compute them, but still what we can do is we can write some relations about these objects. So, for instance, we can write momentum sum rules. Momentum sum rule. So what does it mean? We can write that the integral over all possible x, when you sum over everybody that is in the proton, sorry, here we can write two limits. This is equal to 1. So the total, when you sum up all the partons in the proton, you take the momentum fraction, add it up, what you get is the total momentum of the proton. So this has to add up to 1. And then you can write other things like conservation of flavor. So flavor for the proton. What does this mean? That if you take the integral in dx and take the U content in the proton minus the U bar content, you know that in the protons we have up, down, but we have also always virtual fluctuation. So if you take up minus U bar, you get 2. If you do the same thing for D minus D bar, you would get 1. This is what we mean when we say proton is up, up, down. And if we do this for any other C quark, the strange or any other quark, that is not a valence quark, we have to get 0. So by the way, so the distribution of the strange and the anti-strange in the quark, in the proton, don't have to be the same, but this integral has to be 0. Right? This is what we know. Now, how do we extract this from data? So obviously, rather than looking at collision with two protons, it's much easier if you want to learn about the structure of the proton, you probe the proton in the most clean way you can do. And this is done in deep inelastic scattering experiments. And this is what I'm showing here. This is what I want to discuss next. So this you really see, this is an H1. This was a DAISY machine 95 that I displayed. What you have is you have an incoming lepton that collides against the proton. Then the lepton recoils here. And here something you can build typically something like a jet. And this is how we think about it when we do calculations. So you have the proton, these exchanges, this is the most important quantity for these experiments, is Q squared. We will come over and over again. This essentially tells you how hard is the probe that you're doing of the proton, how hard scattering this is. Right? And this object then recoils. So now I want to write a little bit of kinematics here, and I want to then explain how, a little bit trivially, how you can extract information from data from DIS. So let me write some kinematic properties here of this. So kinematics. So maybe let me draw again the scattering here. And introduce some notation. So this is my hard probe. And then, so this is the proton that comes in with momentum P. This has momentum here x times P. This is a vector Q, and here I have, let's say, any plus or any minus with momentum K. This recoils, so has momentum K prime after the scattering. And this, you see, this is a space-like exchange, this Q. So Q squared is negative. So often we talk about big Q squared, which is minus little Q squared, and this is the quantity that is positive. So when we want to look at the kinematics, so one thing one can start writing is variables that have to do with the full event. So, for instance, the center of mass energy of the scattering, K plus P. This is K plus P. This is, you take this, and this is the center of mass energy of the scattering. Then an important variable, which we will see, is this so-called X per Ken. Now let me just tell you how this is defined. This is defined as Q squared divided by 2pq. And Y is a sort of angular variable. This is defined as PQ over P times K. You see, this is has no dimension, and one can see it has an interpretation of an angle. Now, let's do the same, but now let's write variables that have to do sort of Platonic variables. Platonic variables. So, first we introduce this P hat, which is X times P. And then we have, for instance, S hat. This is simply K plus P hat squared. So this is 2kp hat, because these objects are massless. Then we can talk about, for instance, y hat. Y hat, again, is the same definition, but using p hat. P hat q, p hat k. Now, p and p hat are collinear, so you immediately see that this Platonic variable is really equal to the variable that you have in the full, involves external particles. And another important thing that you can compute is you can compute p hat plus q squared. So this p hat is this one here, this is p hat. If you add q, this is somehow the on-shellness of this object here, this one. But this at lowest order, this is 0. So p hat plus q squared, this is 0. And now, if you expand this, you get the 2p hat q plus q squared or minus q squared equals 0. And now, if you compare this, this we can also write as 2pqx equal q squared. So x equal q squared over 2pq. And these are now the two important relations. Let me write them down. One, you see that this one is really equal to this one. So we know that x is equal to x hat. X is equal to x per Ken, and this y hat is equal to y. Now, why is this interesting? It's interesting because what you can do in perturbation theory is compute the Platonic cross-section. So the Platonic cross-section involves somehow this part of the scattering. So involves these Platonic variables. And this you can compute in perturbation theory. So we don't have time to do it, but if you do it, the Platonic cross-section gets this form, ds hat over dy hat equals, so you have a scattering of a photon on a quark, so it's proportional to the charge of the quark. It's proportional to the center of mass energy. You see that we have a propagator 1 over q squared twice, so 1 to the 4. And then, okay, you have some factors, the coupling constant, and this, of course, you have to do the calculation to know that this is the result. But this is what you get in terms of the Platonic cross-section. Right? Now, what you can do is that you want to compute the Hedonical cross-section from here. So the Hedonical section is what actually you can measure. And so the Hedonical section has instead this form. So The Hedonical section, you can also measure it as an angular cross-section. So what you can measure is the sigma over dy, and this will be the integral over x, the sum of the patterns that you have, Fix in a proton, times y hat. So here you see that you use that y hat is equal to y, so you can compute this part using y hat here. But y is a variable that has to do with the external kinematics, so this is something that you can measure. And now if you even use that x is equal to x per can, you simply can write, for instance, this cross-section in this form, the sigma, the x per can, sorry, per can. So if you take the derivative of this, you essentially get rid of the integral. So what you get is sum of I Fix. Now, so this part in yellow you compute, this part in orange you measure, and so you see that by doing this you can extract this combination of pattern distribution functions here, this one here. So the sum of your pattern distribution function. So here, sorry, I was a bit too. There was an important point. Here you see that there is a charge, QL here. In fact, this part has to go into here, so sorry. Let me write it explicitly. Here we put the charges squared here. And here instead, let me write it explicitly rather than that. Then here what you get is 1 plus 1 minus y squared. And then, okay, times some factors is 2 pi alpha electromagnetic S x b over q to the 4. Okay, so you see that at this point you can extract the sums of pattern distribution functions. Now this combination is really, sorry, and here also I was floppy. This x you put in here. This x is equal to xpj, and this is here. Now this combination really describes the structure of the proton when you do this type of scattering. So it even has a name, and it's called the structure function, or F2, the F2 structure function. This is really defined sum over I x qi squared fi of x. This is the definition of some of the structure function. So for an electron scattering on a proton, this structure function to lowest order has this expression. So we have x times, now the charges, for instance, up has charge 2 over 3, so 4 over 9 times u of x plus 1 over 9 d of x. Okay. So if you scatter an electron on a proton, you can access this combination of pattern distribution functions. And now the question is, how can you measure these two separately? And now to do this, we can use isospin, as we mentioned. So isospin tells you it's a symmetry and tells you that the neutron is like a proton where up and down is exchanged. So this is what you have for an electron on proton. Okay. Now for an electron scattering on a neutron, so here let me write it, this is for the proton now. F2 for a neutron will be also x, and then there will be a. So here also let me put now indices. This is the down in the proton, this is the up in the proton. And here instead I will have 1 over 9, the down in the neutron, plus 4 over 9, the up in the neutron as a function of x. So this is the definition of the structure function. You sum the content down and the up. And now you use isospin. You say down in the neutron is equal to up in the proton. So this becomes equal to 1 over 9, the up the proton is a function of x, plus 4 over 9 put down in the proton as a function of x. Okay. So this here it's where you use isospin. Well, this is really the definition of F2. Okay. And now you see that if you do a scattering on a proton and then a neutron, you have two sets of data, and you can access this. You can access these two distributions, the up and down content of a proton, for instance. And now I also, however, told you that when we say that the proton is made up of up, up, down, this is what we mean. So in particular, we mean that if we take the combination of up minus u bar or d minus u bar, we should get these numbers, 2, and here we should get 0. And now, of course, the photon interacts in the same way with up and anti-up. So there is no way you can probe by doing a deep inertial scattering with a photon. You cannot probe these differences. So how can you probe this type of difference? Well, you have to find a particle that interacts in a different way with up and what is done is, rather than doing a scattering with an electron and the photon exchange, you can have a W exchange. So you have a neutrino scattering, and with a W exchange, and you can probe this type of differences. So experimentally, so what happened is that people started these deep inertial scattering experiments really at many different values of the center of mass energy, different values of Qs and so on, and then perform these combined fits of distribution functions. And you can see that you can at the end get a lot of information on the quark content of this. Now, however, if then you take this and say, well, now I want to check momentum sum rule. Momentum sum rule was somehow this relation where in the X you sum over all quarks in your proton, phi of x, you should get 1. Here you always integrate the momentum fraction. I never write it, but this always goes between 0 and 1. So this should integrate to 1. But you see that when you include only quarks, this doesn't integrate to 1, but rather integrates to something that is 0.5. Right? So the quarks actually carry only half of the momentum of a proton. Okay, this statement depends, of course, on the energy and so on. But we know what is also there in the proton. We have gluons, and the gluon content is really very important. It carries a lot of momentum. But you see that there is no way you can extract the gluon distribution by this type of experiments, because all these photon W's and so on don't really interact with gluons. So this is the next topic I would like to discuss. How do you probe gluons in the proton? But maybe I have a short break here and see if there are questions so far. I don't see any.
Yeah, there is one.
There is one.
Yeah, just to see if I understood correctly. So this F2 function we find for the proton only containing quarks is because we are looking at a scattering which cannot involve gluons as partons. Is it correct?
No, so F2 is really defined now, the structure function. So here I did not say what this I is. So I really involves everybody that is in the proton. The structure functions you sum over everybody here. But at lowest order, when we do this calculation, we think about this proton made of up, up, down. The lowest order approximation you can make is say this has up, up, down only here. Right. But the structure function contains really everybody. Now the point is that you cannot, however, access any information on the gluon. So if, sorry, maybe more specifically, so F2 here contains also gluons, but these gluons will actually not contribute here because there is no scattering here. The gluons in this picture don't enter the scattering. So in the process that you measure, the gluons will contribute. It's like at the LHC, if you want to compute a Higgs boson, you know that you need two gluons. You can have also quarks, but they will not produce the lowest order approximation Higgs. Or hydronium will be produced by QQ bar, but not by gluons. So they don't enter in this. But of course, this is somehow doing the simplest, the lowest order approximation you can do. To somehow, I wanted to introduce here how you can become sensitive to these distributions in these experiments.
Okay.
But important point, yeah, it's that these deep elastic scattering experiments are not sensitive in the lowest order approximation to gluons. In fact, this is what I want to say now. I mean, gluons enter very important effect. When they enter when you compute radiative corrections to this, when you start moving from this low order picture to the picture where you emit from this quarks.
Okay, thank you. It is more
Giulia, since you asked the question, your audio got worse, like the usual ovattamento.
Much worse? Let me see. Now?
Well, probably now it's going better.
Is it better?
We'll see while you answer the next question, which is on the chat. If you want, I can read it, otherwise.
So how well are the PDFs known? Are they the main source and so on? Yeah, so I will come to this. This is what I really want to cover in, so maybe if I did not answer the question at the end of the lecture, we can come back to this. But I hope to manage to show something about this, how well they are known and so on, and discuss this. Maybe the tablet went to sleep. Is this, oh. So I will, yeah, I will postpone this. Okay, so to account for gluons, what we have to do is to discuss radiative corrections to this. And this will also bring us to the point that was raised yesterday, what happens with singularities when you have radiation from the initial state. So if we, let me draw again the process that we are discussing here. This is this deep elastic scattering. So here we have, these are leptons. And we can think about this as a simple photon. So these particles have no QCD interactions whatsoever. So, and here, this is my proton, this is the parton that enters. Notice that they are really aligned. What I call here XP, I cannot draw it aligned. Somehow it's often drawn like this, but they are really collinear to each other. No? This the parton that enters is scattering. Now, when you do corrections to this process, what happens is that, well, all you have to do is like in the final state, you do virtual corrections, so diagrams like this one, okay, and real emission corrections. Now, let me simply get rid of this and draw the real emission correction here. Now, so this momentum is XP, what enters, which I call P hat. And now you see what happens, that this gluon will carry away some momentum. So now the particle that enters the collision, let me call it Z times P hat, and the gluon will carry 1 minus Z P hat energy fraction, approximately, at least in the collinear approximation. So now what you can do is you can treat again this part as we did last time in terms of perturbative calculation, perturbative QCD, draw the amplitude, square the amplitude, and so on. And what happens to the Platonic cross-section at the first order in the coupling constant, so let me call it sigma 1, meaning first order in the coupling, is that again it has this CF alpha S over 2 pi. And now let me write it in the form. It will, you integrate over this radiation variable. So one you can choose to be Z. The other you can choose, for instance, to be typically, this is written in this form. Rather than an angle, one can use a relative transience momentum of the gluon with respect to the emitter. The relative transience momentum in the small angular limit is simply the angle squared times the energy squared. So if you want, it's essentially even the same thing, but this is often written in this form. And then, okay, if you do the calculation, you see that you get a function of Z. And then we get a Platonic cross-section, which I write as sigma 0. So this factorization, as we had before, this, maybe let me, so this part has to do with radiation of the gluon. And then the rest here now has to do with the hard scattering. So sigma 0. But now you see what happens. Sorry, here I'm going into that. So now this is my real contribution, and this is my virtual. So this sigma 0 is the Born level. They are the same. So it's a cross-section you would have without the red gluon here. And as before, we see that they have the same form. One is positive, one is negative. Typically, they cancel. So if you take the limit where z goes to 1, you see that there is this nice cancellation in the, so the limit z to 1 corresponds to this gluon being very, very soft. And now you see that this cancellation, when you have collinear emission in the initial state, this cancellation doesn't happen anymore. And it does not happen because this hard scattering here happens at a different energy if you have initial state radiation. So the radiation that is somehow emitted before the hard scattering. So what can one do with this? Well, what you can do is you can start, first of all, you can put a cutoff in this integration. You say, well, here, I don't know if I can write in this now anymore, no. So let me rewrite it. Sorry, I'm not too skilled with this stuff. So what you do is, okay, you have this CF alpha S over 2 pi, an integral in Vz, an integral in the case t squared over kt squared, and now you put an explicit cutoff on this lambda squared. And here you still integrate up to your high energy scale, let me call it q squared. Then you have, let me also introduce this notation where I call this p of z. We will see later even why this is. And maybe in, let me also write it directly in this form. I call it p plus. So this here, this is a plus prescription. The plus prescription somehow was introduced in QCD, essentially because every time you have this, you compute the real and then compute the virtual. You see the real and virtual have the same form, but the virtual has to be evaluated at z equal 1, because when you have a virtual correction, it can never take away energy fraction. So the plus prescription is defined in this form, an integral in dz, a function plus prescription with any other function is equal to the integral 0, 1 f, sorry, in dz, f of z of g of z minus g of 1. So what this means here, when I put the plus, it implicitly has this subtraction of the virtual correction, right? So far I have done nothing. I put a cutoff and use this plus prescription to save on writing. So the collinear divergences are really still there. Now what you can use is you can simply see that this is a logarithmic integration. So let me start a new page always. So then you can use that simply naive. So this will give you a log of q squared over this lambda squared when you do this integral. And now you know that you can write this as q squared over any scale you like. Okay. And now what you can also do is you can essentially approximate something that your cross-section contains the sum of these two terms. But to the order at which you're doing the calculation, so to order alpha, you can also write it, so this, let me write now, sigma 0 plus sigma 1 can be written as 1 plus this alpha over 2 pi log of, let me write it in red here, mu f squared over lambda squared, if this P prescription times 1 plus alpha x over 2 pi log of q squared over the scale UF times the sigma 0. And now what you can do is that you decide, if you want arbitrarily, to reabsorb this part into your PDFs when you compute your cross-section. And this part, instead, you keep in your Platonic cross-section. So you redefine your pattern distribution function. In the same way as the coupling was redefined, you define f of x, now mu f, now you see this depends explicitly, as somehow your Bayer or without collinear divergences function, 1 plus alpha s over 2 pi, then mu f squared over lambda squared, which is 2 plus 6. And then your Platonic cross section instead, which now also depends on the energy, but also on this additional scale mu f, has this term now alpha s over 2 pi ln of q squared over mu f squared times the sigma 0. Okay. So in essence, these collinear divergences are there. They can be absorbed, however, in a universal way in the pattern distribution functions. So what happens, as before for the running coupling, we see now that the cross sections depend on this so-called factorization scale, now not renormalization but factorization scale. Explicitly in the Platonic cross-section, we see that there are explicitly these logs, and implicitly in the pattern distribution functions. So these two objects don't evolve independently. So you have to also use, in a consistent calculation, you have to use the same scale in the two parts, because the interpretation of this scale is that all collinear emissions below that scale have been absorbed. And so you would essentially leave a gap in your calculation if you use different scales. The other thing we see is that in the same way as when you renormalize a cross-section, you get a log of q squared over mu r squared. Here you get a log of q squared over mu f squared. Now, in a generic calculation, this q squared is essentially the hardness of the process. So if you take a scale that is much, much below or above the scale of your process, you will see, you know that you will get large logs from this type of corrections here. So these logs would then invalidate the fact that alpha is small, and your perturbative calculation would not converge very well. That's why somehow one always chooses a scale that is of the same order as the hard scale of the process. So if you do Drell-Yan, a typical scale would be the WZ mass. If you do Higgs, the mass of the Higgs, and so on. But of course, when you go to more complicated processes, this choice becomes more and more difficult. So in essence, we started with the formula, with the pattern model formula, and that formula, as I said, was a bit is incomplete, but somehow once you include radiative correction, the correct formula that now we always use, our master formula if you want, is this one, dx1, dx2, f I of x1 mu and then you have a Platonic cross section that depends on the energy, Platonic energy, so it's on x2s, and it depends on the factorization scale mu. So somehow in the Platonic model you don't have this dependence on the scale, but this is really crucial. Once, so if you do radiative correction, you don't have this the pattern model simply breaks down. So I don't know if this was clear at this point. So the whole point is that when you have collinear emission from the initial state, they don't cancel because you're in the cancellation between real and virtual. But you can absorb this in a universal way in pattern distribution functions. They become scale dependent. And by doing this, you introduce this factorization scale, and to some extent, it plays the same role as a renormalization scale. And they both have to be of the same order as the process, so very often they are set to the same scale in practical calculations. And it's really, as for the renormalization scale, if you do a calculation at a given order, so for instance, what I showed you here, very naively, you see that here I neglected terms that are alpha s squared. When I do a product here, I would generate terms that are higher order in alpha s. Right, so the dependence on your scale in your calculation is always one order higher to the order at which you did the calculation. So here there is an explicit dependence that is alpha s log mu f, but this cancels exactly with the dependence that is in the pattern distribution function, and the residual dependence is really one order higher. Okay. And so this is then the formula that our master formula that we always apply. If you do deep elastic scattering, you have one integral, and at colliders you have two. Okay, so if there are no more questions, I would like now to talk about the evolution of this pattern distribution. Now, there is
one question. There is one question.
Yeah.
So, Jürg?
Hi, can you hear me?
Yes.
Okay, I wanted to ask, this formula is often known as the factorization theorem, but I mean, I've also read about the factorization breaking effect, and I wanted to know if you can just give us like a small summary of how important these effects are and how general this formula is believed to hold today.
So, the formula is proved only in very simple context, really formal and complete proof. There are other proofs or arguments and so on. But it is true that it's used in a much broader context compared to really formal proofs. Okay. On the other hand, when people really started looking and trying to see when will factorization breaking terms really arise, this seems to be really a very high order contribution. So beyond, for instance, there is a paper that claims factorization breaking terms at order alpha cube if you have at least 4 QCD particles, so two going into 2. So at the moment, for practical purposes, this holds. But it's true that it would be nice that you have more complete proofs of this factorization.
Okay, thank you.
So Giulia, now I have enough statistics to tell you that every time you answer a question, your audio changes somehow. I don't know if you switch off and on the microphone or something like that.
No, I do nothing, but so I can always choose between same as system or MacBook speakers. Now it's better.
Yeah, probably it is. Yeah, it seems so.
I don't know. I switch back and forth, but now it's
yeah, but we can hear you now. So if there are problems, I tell you.
Okay.
There is another question in the chat, though.
Sorry?
There is another question in the chat.
Yes. It's true, absolutely true. The master formula is not exact. So we have power corrections. Yes, I mean, we have, yeah, absolutely. This is up to non-perturbative power corrections to the formula. Yeah. Okay.
Yes, you can go ahead. No, yeah, there are other questions.
Yes, so the PDF extracted from data are the renormalized ones then, yes. Okay, so okay, so now I told you we cannot compute PDFs, so you measure them, but then it would not be very useful if you measure them in a deep elastic scattering experiment and some energy and you cannot use them somewhere else. Really, the nice thing about them, like for the coupling constant, is that what we can compute is how the pattern distribution functions evolve with the scale. And I want to try to illustrate this. And to illustrate this, let me, so suppose that you have a pattern. So you're looking for a pattern. So what can happen to this? This pattern, so now I'm being a bit naive, but so here I have a pattern that has momentum fraction x prime. It undergoes a collinear splitting. And so this one, after the collinear splitting, let's say this will have momentum x, which is z times x prime. While here I have my pattern with momentum x, and this undergoes a splitting. So here I will have z times x, 1 minus z times x. Okay. So what can happen? So a pattern that I have with momentum fraction x can disappear because it splits, or it can be created by somebody else. And so one can turn this into an equation that now I will try to write. So essentially the way in which a pattern at a given scale x and mu squared changes with mu squared can be written as, maybe I try to start with the negative, with the minus. So I had this pattern with momentum fraction x and mu squared, but this undergoes a splitting with a splitting function. Now I call it P of Z. It splits with this splitting probability. And now this, I mean, was there, but this, the pattern is not there anymore after the splitting. So this is a negative contribution. And then instead I have a positive contribution where I integrate over all possible values of x prime that I had. And then I have a splitting with energy fraction z, and I also integrate over z, this can be anything. So I have this alpha s over 2 pi, my p of z, my pattern distribution function with momentum x prime and mu squared. And now I require that what I wrote here, that x is equal to zx prime. Okay? And so again, I integrated over all possible kinematically allowed values. Now you see here I have only one integral, here I have two, but I have a delta function. So I can get rid of the delta function. So get rid of the x prime integration, for instance. So this becomes then the integral in this z from x1. I have alpha s of 2 pi z, and I get x of z mu squared minus, and here I have exactly the same thing here. So this means the same. Okay. And now you can see I can use the plus prescription that I like before. You see that now these two terms again have exactly the same form, but this is evaluated at z equal 1, and this has this x over z. So I can write it in this form. F over 2 pi p plus of z f of x z mu squared. Okay. We'll use again the plus prescription. Now I derived this a bit in a very naive way, but this equation that I wrote here, this one, the fact that the change in scale with a pattern distribution function is given by this expression is known as the Diglap equation by Dorchitzer, Grigov, Lipatov, Altarelli, Parisi, was formulated in the 70s really. And it's really one of the master equations that we have in QCD. So it tells us we cannot compute pattern distribution function, but we can compute how they evolve from one scale to another. So you can measure them at low scale in the classic scattering and then use them in high energy experiments. Right. Now, of course, here I wrote this picture in a little bit a naive way and so on, but if we really, so I used different colors, and the red was some of the pattern we were supposed to focus on, but really the Diglap equations are very complicated. So let me write it now explicitly. So here. So typically what you do is you introduce it. sorry. You introduce a splitting function in this form. So we have different species of particles. This is what makes this somehow really complicated also to solve. Now I call this here B, C. This has Zx, this is 1 minus Zx. And this, when you compute this, the square of this object in the collinear approximation is what we call the PBA of Z splitting function. So the second index is usually the pattern that branches, and the other one specifies the identity of B. And then the third one is implicit, essentially. So this is our standard notation. We call this splitting functions. And then when you write the equations, taking into account that there are all the possible species, of course, this equation is this, or maybe I can simply, no, well, let me rewrite it. You have to essentially put indices in this equation. So this becomes mu squared dfi of x mu squared over d mu squared. This will equal to the sum over j integral from x to 1 z over z p I j z fj of x over z of mu squared with the plus prescription. So you see that this is really a system of coupled integral differential equations. So the gluon, for instance, affects the propagation of the up, and the up can affect the gluon, the down, and so on. So somehow solving these equations is really kind of very complicated. And just to say this, often, because we don't like to write these integrals and so on, we write this just to introduce a notation. This is just a matter of notation. We call these convolutions. So we write simply like this, fj. So we don't write this z, the integration variable explicit. This is just to write this in a simple form. But yeah, I mean, it's somehow a difficult system of equations. So we started a bit with the question, how does one measure the gluon here? The gluon you can really access because it has a large impact on how it affects the evolution of the quark distribution functions, for instance. And so now you have all possible splitting functions. So by looking at that example, so we looked at the example where there is an incoming quark that emits a gluon. Right. And so this has momentum z, 1 minus z. This is a splitting function where there is an incoming quark and remains a quark. So this is what we call PQQ. And at lowest order, this is of course the same if you have quarks or antiquarks. And it has this expression, 1 plus z squared over 1 minus z, with this plus transcription. And then and so on, you have different functions where you have an incoming gluon that splits into a quark and an antiquark, or you can have this, which is kind of related by some symmetry and so on. Or the most complicated is, of course, where you have a gluon going into gluon. So now maybe I will give you my slides, so there is no point in writing these expressions really explicitly here, I think. Maybe let me only write this one. So this splitting function here, this is what we call P. So this has this property. Let me simply write this one. So you see that this function is based on trivial properties. For instance, this one you see has to be symmetric in z and 1 minus z, obviously. But also one of the things you see is that here there is no singularity here. So it means when a gluon splits into QQ bar, there is no soft singularity here. But there is this kind of singularity is there instead in this case, right? So there are always singularities which involve soft gluons, and this is why gluons are always more important also at very low x. Okay. Now, so we discussed this also this relation on the slide. So maybe this is something that I don't do, but maybe it would be good if you try to do it as an exercise. And then I will give you slides that guide you through this. So one can prove that the fact that the integral of x, of f of x, f u of x u squared minus f u bar of x u squared, that this quantity is constant. This is if and only if the integral in the set of pqq of z is equal to 0. So on one side, you can compute this and explicitly verify that this is the case. And then you can say, well, then I have proven that f of u minus f u bar is constant. As we wrote this as conservation rule, so this I have to hold. On the other side, you can say, well, if I know that this is the case, I can use it to extract some parts of my splitting function. So the splitting function typically involve a real and a virtual term. And I told you the virtual term is encoded in this plus prescription. So this somehow you implicitly say that this is the case. But you can explicitly then compute this virtual correction by simply using that relation, by using the fact that you know that this has to integrate to 0. So for instance, as an exercise, you could try to show that you can express this pqq of 0 also in this form. This is somehow how you often find this written. Note that the plus prescription now applies only here. And then there is a delta term. Delta term explicitly means this is a term that lives at z equal 1, is a virtual correction, and so on. And you can also try to compute this also in the other cases. So you can extract this essentially virtual correction without doing any loop integral by using this conservation rule. Now maybe I don't do it here because otherwise we don't get too far. But so the expressions that I wrote down of these PQQs are the lowest order expressions. And so these were, I mean, soon after QCD was developed, these functions, these PAB at lowest order were computed by Altarelli, Parisi, as I mentioned, Diglap, Grigov, Lipatov, Dochitzer, somehow in the 70s. Then the first order correction was computed in about the 80s by Kurtschif, Formansky and Petronzio in the 80s. And the second order correction was computed much more recently. So it took almost 25 years to compute the next to leading order correction, so the two loop. So when you take this and draw all two loop diagrams, all two real emissions and so on. But this is, of course, this is next to is the state of the art today. We will see more about this tomorrow. So this is absolutely crucial for today's applications. So I'll, yeah, I mean, this is just a picture really, but I wanted to show it because it's a way one can think about it. So when you increase the scale, what does it mean? That you somehow, you can think about increasing your resolution power. So you see more into these virtual fluctuations that are inside the proton. So you probe more deeply into the structure of the proton. Okay. And yeah, so now what I would also like, I would like to show you some things that help a little bit illustrate how this, so this is this function F2 that I mentioned. So the structure function, and you can see now, you can clearly see here the effect of, so this plot is very compact. It shows you how many data were taken and so on. And to illustrate, to put different data on the same plot, you see that these data are often scaled by function so that you can stack them all together. But it shows this F2 as a function of Q squared and at different X values. Right? And now the Q dependence on this is really what comes due to this perturbative calculation. So in the pattern model, this would be X dependent but not Q dependent. And so gluons here really play a crucial role. You see at low low x, this is where you're really dominated by gluons, and you see this very steep dependence of these functions. So gluons have really an important role in determining this evolution. And let me also show this here, for instance. So here you see, okay, this, first of all, you can see somehow the typical shapes of these distribution functions. So up and down, the valence distributions have always this type of shape. So they're peaked at a relatively large x. So about x equal 1/3 approximately. Up is about twice the down in the proton, but then they become smaller at small x. And instead, the C-quark distributions pick up at the small x and become much more important. You see, for instance, the gluon here is even divided by 10 to put it on the same histogram. Now, from left to right, you see that these are exactly the same distributions, and all you change is the scale here. You see here, this is mu squared 10, and here mu squared 10 to the 4 GeV squared. Right. So you increase Q, you somehow probe more and more deeply into the proton, and you see these virtual fluctuations, important and low x, and you see this. So it's not a small correction. This evolution is really crucial to, if you would use a PDF at a different scale, it would completely not match. So this is somehow really very important in this picture. And maybe the other plot that I would like to show is this one a little bit. So this again tells you, so this green that you see is here. Here was this Kinematics scattering experiment that really performed a lot of measurements. And this is the plane in x and q squared that could be accessed by that experiment. And now instead the blue here is the kinematics that is relevant for the LHC. And you see that somehow measurements were done at much lower q squared here, but this is not important because you can do the D-gap evolution and you can move vertically up in this plane. Right? The other thing that one can see about this plot is that, okay, of course, if you want to access an object that is more and more massive, so if you go to very high masses, of course, you have to access very large x values, because typically, x1, x2 times the center of mass energy has to be equal to the mass squared of the object you want to produce. So the more heavy the object, the more large x is important. But also large x and small x become very important when you go forward and backward in rapidity. So this is shown here. I will discuss exactly what this rapidity is. But large and small rapidities means very forward and very backward. Now, if you have, for instance, a Z boson that is produced very, very forward, it must have come from a collision that typically has a low x and a very high x. Or one, so it has to be very asymmetric, this collision, right? Then it goes very forward, very backward. So whenever you're interested in looking in this forward backward, you're interested in large rapidity regions. And maybe the other plot I have here is, yeah, this one. This also shows a little bit, yeah, we know now we have the LHC, but people are, of course, thinking about future colliders and so on. And so this is one of the many plots that you can see. So this shows the plane. Red is here now what is accessible at the LHC, and blue is what would be accessible, for instance, a future FCC machine at 100 people. In terms of talking about new physics, so you see you have, for instance, of course, you have more energy, so you can access Z primes that are more heavy and so on. Okay, so now I would like to say a few words about, so I talked about these very old extractions. And of course, these PDFs are the input in any cross-section that you compute at LHC needs a Parton distribution function. So there has been a lot of progress from the very first fits that were done to the very more modern ones. And so typically, first of all, these PDFs are not numbers, they are functions. So how do you fit a function? The first thing people did is to take a parameterization. and fit a few parameters in this function. So you know this kind, you have these shapes that I showed you, so you can find a parameterization that fits relatively well, and then you can, well, again, you can fit your parameters and so on. But then, of course, you have a problem that maybe your parameterization is a bit too rigid and doesn't really hold in some different regimes. So one of the more recent approaches to this has to do so recent progress. What does recent progress in this field really include? So one is the approach of using neural networks. This really allows for a much more flexible parameterization, essentially, of your function. So you don't introduce a bias and you have to stick to this parameterization. Then a much improved assessment of uncertainties. Now, I don't have time to show you too many plots, but if you look at very old determinations of PDFs, you could see that there is a determination with some uncertainty, and then the next determination that includes more data, somehow the uncertainties were not overlapping at all, right? So there were different jumps and still very small uncertainties. So now there is really a lot of work has been made in somehow devoted to having realistic determinations of the uncertainties associated to the parameterizations. The other thing, of course, is to include more and more data, new data from the LHC. So really more and more data is being included continuously, the more data you have. And then improvements on tools and methods on how you do these fits. Other things include new PDFs. This is something I also worked on. For instance, we always think of a proton as made of quarks and gluons, but if you have quarks, the quarks obviously also radiate. And so there is a PDF, for instance, that has to do with a photon content in the proton. And so people got interested historically on this PDF when a few years ago there was an excess in diphoton production. So that people were thinking about the resonance that interacts strongly with photons in the final state. And I started worrying, what about production from photons from the initial state? But the photon PDF, in fact, enters also Higgs cross-sections and was dominant uncertainty in many cases. Then, even more recently, we looked at, for instance, lepton PDFs. Again, if you have photons, the photons can also split produce leptons. These PDFs are very small, but at the end, you can do something also with them, some in physics. Now, what are the issues that people have to have concerned about? What are always the problems in these PDFs? Or some issues where people sort of debate and so, for instance, which data to include? Which data? So, in particular, one would say, well, you include all the data, right? Then you have a better description. Well, but what happens if some data is not compatible? If you have a measurement that is not really compatible with another one, how can you include it in a fit? It can be a disaster. So how do you deal with incompatible data? Is it fair or is it not fair to enhance the relevance of some data? Some data you think the measurement is more solid, and so can you enhance the relevance of some data or not? Then there are issues about when you talk about, for instance, heavy quarks. How do you treat the masses in the initial state? You have thresholds, and what theoretical approach you take there? Different groups do different things. Then what else? So there are sometimes, if you do a fit, you can get an unphysical behavior, in particular where you don't have data. So very close to very small x or very large x. If you just allow your neural network to do what it would do, you could get some unphysical behavior. So how much physics do you want to put in? And how much do you want your fit to be completely unbiased from what you do? How do you interpret uncertainties? So PDFs come now with an uncertainty, but what is it? Is it 1 sigma uncertainty? And what is really the meaning of that? In fits that include LHC data, you typically could decide to fit alpha S and the PDF simultaneously. This is done. Or you could take alpha S. You can say, well, alpha S now is determined precisely from lattice. I take it from there and fit only the PDFs. So you see, there are really many issues that are discussed and the different groups. And now there are different big collaborations that fit these PDFs. And sometimes they do different choices with respect to this. So here, sorry, I just spoke and I didn't write anything, so I simply get rid of this. And yeah, so these I think are the main issues discussed recently. Now I think I want to introduce, and then I want to show one example, and then I'm really close to the end. Is often rather than talking about PDFs, we talk about luminosities. So what is a luminosity? Let me write the definition of luminosity, and then I hope you understand why this is really useful. And so luminosity, typically called Lij. So this could be, say, the gluon-gluon luminosity or the quark-quark luminosity. This is defined as the integral in dx1, dx2, and they always go between 0 and 1. Fi x1 at the given scale, Fj x2 at the given scale, and then you require, sorry, times delta of tau minus x1, x2. So tau is essentially the ratio of your Platonic center of mass energy divided by S. So remember, this S hat was x1, x2, S. So tau is the product of x1, x2, and tells you essentially how massive an object you can produce, right? So this, the luminosity, is actually what enters the cross-section. Sigma, the function of S, can be written in sum over all ij's. Then you have an integral in d tau. Okay, the factors of 1 over S you can work out, they're also not so relevant. So and this is a function of, sorry, well, let me write it in this form, times S, so let me write it in this form, times S, sorry, S S hat sigma hat ij. So in essence, the luminosity contains already the information from both PDFs. You know that the collider, you need to collide two and to produce something. For instance, if you look at Higgs production at lowest order, you're really interested in the gluon-gluon luminosity. And yeah, tau gives you the mass of the object on the final state that you're producing. So in this here now I want to show an example of these uncertainties and so on. So these are three of the main collaborations to this kind of fit. NMPDF, which is the one based on neural networks, and the other two groups, CTEC and MSTW, that somehow use a parameterization, but now it's a much more flexible parameterization and so on. And now you see that the region where the Higgs is produced is somehow close to here, right? And in this region here, you see that these uncertainties were really not overlapping nicely. After including more data, in particular including LHC data, you see now this is a newer fit, and you see some of this beautiful overlap here. And now this somehow mounts to a change in cross-section. So this again, these are older numbers. For the, you can try to compute how many Higgs bosons you have for the total Higgs production cross-section. And you see here that different PDFs, there are two numbers for each, using two different values of alpha. So here you see two values here. So you see on one side, the value of alpha makes a big difference. If it's 0.017, 0.117, 119, and this is about the uncertainty we still have today. So this makes a difference. But also the set of PDFs used to be quite different. So first, the recommendation was, okay, one has to be conservative, you have to take the envelope of all these global fits. Now you see that more recently, this the envelope is somehow not needed anymore because this becomes more and more consistent. So this is just one example that I wanted to show on this. In principle, one can really show many. Now, there was a question about these uncertainties. I don't have many other plots. I can show maybe more tomorrow or so. But the bottom line is a little bit that whenever there are data, all the PDFs agree very, very nicely now. In the regions where there are less data, typically very large or very small X, the uncertainties become larger, but they don't even, sometimes they don't still really overlap and so on. So I think I'm coming to the end now, and let's see if there are questions. No questions. So I hope what you should remember of today is that you can start with this Parton model, this probabilistic interpretation. There is PDFs don't depend on the scale, but then when you do calculations, there are collinear divergences, this breaks down. Then you factorize this like with alpha S, and you introduce the scale-dependent PDFs. So Parton distribution functions, Platonic section depend on the factorization scale. And you can compute using these DGLAB equations that I somehow a bit naively derived here. You can compute how the PDFs vary with the scale. And yeah, this universality that we always use. We extract PDF somewhere, evolve it, and use it somewhere else. This is why this machinery is very powerful. And yeah, today we do fits using global data. So now all data is included in the fits, and this is really done in a very professional way. Other questions?
Well, they may be thinking to ask the questions.
But you can still hear me. When there is no reaction, I don't know if I'm talking to an empty audience. But okay, I mean, we have a discussion session later today. But I think maybe it's a good point to stop here. And then next time, I'd like to start to explain a little bit calculations at the LHC, how they are done. And,
so maybe I have a question. Maybe you mentioned it and I missed it. It may be. But did you mention the issue of the correlation between, I mean, the data that you use to fit the PDFs, and then if you want to analyze this data to search something else, then there is a correlation. So you have to have sets of PDFs where you exclude some data.
So you remember, yeah, sorry. When I was mentioning the issues when you do the fit, this I thought there's something else, but I thought, oh yeah, this is one of the big issues. So first of all, how do you make sure that you don't fit the new physics into your PDFs? And how you, yeah, as you say, when, how do you treat these correlations? These are, okay, this is a big issue, right? In what you mentioned.
Yeah, it was more of a remark just to
yeah, no, it's very important.
There is this to take into account. And
no, this is absolutely crucial. And okay, I mean, so what do people do? So, for instance, if you want to make sure that you don't fit new physics in your PDFs, or what you always should do is that you remove some measurements from your fit, and the fit should not change drastically, right? So the consistency of when you remove single data sets, your fit should not be affected by. But this, of course, if this is the only data set,
so for instance, what we did when we studied new physics in Delian, we could use PDFs where Delian data were excluded. So, and then check what happens if we include or exclude Delian data. Exactly. And then if you don't see a big change, it means there's no correlation, typically exactly. Because the PDF extraction comes from a different region in the phase space with respect to the one where you expect new physics. Exactly. It's a check to do. So yeah. In this view, it would maybe be useful to develop in the future some, how can I say, some PDFs for users where users can somehow do a quick PDF refit excluding the data he wants to exclude, no? Because it's not given that everything is available already, no?
Yeah. Absolutely. And I think people are thinking in that direction. Yeah.
Very good. So if there are no other questions, thank you very much, Giulia, and we will see each other with you.